Hi, welcome back to our lecture series. This is going to be an introduction to one of my favorite topics in mathematics, partial differential equations. I hope you enjoy. Let's review some basic concepts. A function can have more than one independent variable. For example, we will call this function, f of x and y, two-dimensional, since it varies with respect to two variables, x and y. It can be thought of as plotting out some surface over a two-dimensional plane. Formally, this means that it maps an element of R2, the two-dimensional real numbers, to some element of R, a one-dimensional real number, or scalar. Recall the definition of a partial derivative. If an equation has multiple independent variables, we call differentiation with respect to one of these variables a partial derivative. We denote these using a kind of curly D notation. In this example, for our two-dimensional function f, we see that there are multiple combinations of partial derivatives for each order. There are two possibilities of first partial derivatives, 3 for second-order partials, 4 possibilities for third order. This number grows large as the order of the derivative grows. Similarly, the number of possible nth-order partial derivatives grows with the number of independent variables of a function. Now imagine a differential equation that has terms for partial derivatives with respect to two or more independent variables of a function. This is a partial differential equation, or a PDE for short. A solution of a PDE is therefore a function of that many independent variables whose partial derivatives satisfy the equation. Just like with ordinary differential equations, we say that a PDE is linear if it contains only linear terms of the solution function and each of its included partial derivatives. Otherwise, you have a nonlinear PDE. If the PDE is linear, it can be thought of as a linear partial differential operator acting on a function. See, for example, the equivalency of these representations of a PDE. Similarly, a PDE can be either homogeneous or non-homogeneous in the same way as an ordinary differential equation. If we take all the terms involving the solution function u to the left-hand side of the equation, it is homogeneous if the right-hand side is 0. It is non-homogeneous if the right-hand side is some non-zero function of the independent variables. In order to clarify some basic concepts, let's begin with a reasonably simple form of a PDE. This is the general form of a linear second-order PDE in two independent variables, written here as x and y. In general, the coefficients a through f are functions of the independent variables. So is the non-homogeneous function g on the right-hand side. The solution of this differential equation will in general be a function u from some domain I to the real numbers. Here I is a subset of R2, the two-dimensional real numbers. Second-order linear PDEs can be classified by type, using an analogy with the geometrical figures known as conic sections. These are the 2D planar shapes that you obtain if you take an arbitrary cross-section of a solid three-dimensional cone. All conic sections can be written in general as a quadratic, that is second order, polynomial in x and y, with leading coefficients a, b, and c. The so-called discriminant of this quadratic determines the shape of the conic section. If b squared minus 4ac equals 0, then the conic section is a parabola. If this quantity is less than 0, you have an ellipse, or as a special case, a circle. If the discriminant is greater than 0, you have a hyperbola. Returning to our second-order PDE, we find an analogous method of classification. For a PDE of this form, if b squared minus 4ac equals 0, we say that the differential equation is parabolic. If this quantity is less than 0, the PDE is elliptic. And if it is greater than 0, then the equation is hyperbolic. This classification system is deeper than just an analogy with conic sections. The solutions of the three types of second-order PDEs show fundamentally different behaviors, which means that the physical systems which they describe also behave fundamentally differently. For example, elliptic PDEs, such as the Laplace equation shown here, tend to have solutions that are infinitely continuous and differentiable everywhere, no matter what. That means that they will instantaneously smooth out any discontinuities in the initial and/or boundary conditions given for the system. Parabolic PDEs, like the heat equation, will tend to smooth out over time. That is to say, if you begin with a discontinuous field, for example, a temperature distribution, the field will even out and become more continuous as some time-like variable evolves. Hyperbolic equations, on the other hand, retain any discontinuities of functions or derivatives in the initial or boundary data. One example is the so-called wave equation. If you start with or apply a continuous wave to a system, the waveform should remain continuous as it traverses the media. However, discontinuous waves, like shock fronts for example, can propagate discontinuously through a wave field which is modeled by a hyperbolic wave equation. Thanks for watching this introduction to one of my favorite topics in applied mathematics. Stay tuned for more content.